Nodes 2023, GDS, and Gen AI, Graph Data Science. I am here today with my esteemed colleagues, Dan Bukowski and Alex Gilmore, and they're going to be taking you on the Graph Data Science with Gen AI journey. Welcome, guys.
Good morning, good afternoon. Glad to be here.
Yeah, good morning.
I tell you, I got a preview of the presentation today, so I'm really excited about what's coming up, and I think everyone's going to really enjoy it. No, I am. I'm genuinely super excited about this. I'm at DockerCon right now and have been raving about it, saying, make sure that you watch the replay. So without further ado, I will let you guys take off.
All right, great. Thank you, Allison. Hello, everyone. Thank you for joining us today. As Allison mentioned, we're both thrilled to be here talking about graph data science and generative AI. This presentation is going to be based on a project that we've been working on for several weeks. Are we getting an echo? Sorry about that.
I don't think so.
I do
Sorry
not
about
hear
that.
an echo.
Okay, I'm very sorry about that. I was getting an echo from the replay. Okay, so let's we'll just keep going. So let's keep moving forward. Real quickly, we just want to introduce ourselves. My name is Daniel Bukowski. I'm a graph data science customer success architect here at Neo. I focus on the graph data science library and really work with existing customers to help them implement and use the library for a variety of projects. And Alex, yourself?
Yeah, and I'm Alex Gilmore. I am a associate consulting engineer on the professional services team here at Neo4j. I've been with the company for just a few months now. I recently transitioned from the healthcare field earlier this year, but I've had a great time working on the data science projects here, and Dan's been great to work with on this project. So very excited to present today.
Also, as part of this, we do want to recognize real quickly just several of our colleagues. We're going to be talking about a project we've built internally, but this was not just the two of us. So Ravi, Ken, and Dave, as well as several of our colleagues who've helped us build it and as well as test it internally. So we would not be here sharing this presentation without a lot of help and collaboration across Neo4j. So very grateful for all the assistance. And so what are we here to talk about? As Allison mentioned, the high-level topic is graph data science and generative AI. And what we really want to focus on is how you can use knowledge graphs and graph data science to analyze and understand and improve an application that you've built using a grounded large language model. And so that's what we're going to focus on: building a high-quality data set, logging the LLM interaction, so how your users are conversing with the agent, and how you can log that in the same knowledge graph as your grounding data, and then how you can use the graph structures and the graph data science algorithms to improve the performance of the large language model. We are going to touch on how we built the application, but that really isn't the focus of the presentation here. And there's several other resources, both on YouTube and elsewhere, that will point you towards for the details around building an application grounded on a knowledge graph. But before we even get into that, just a really quick note about grounding. Alex, do you want to touch on this?
Yeah, absolutely. So this entire application is built around the concepts of grounding and retrieval augmented generation. And so retrieval augmented generation basically allows your LLM rather to access information that it otherwise would not be able to access. And not only that, but also allows finer control over that information as well. And so in this project, we're grounding via a knowledge graph in Neo4j. And we found that by using this data source, our knowledge graph, we're able to get much more accurate responses with reduced hallucinations as opposed to using just like a vanilla GPT model. And I think it's also important to mention that some of these models can now do a internet search. They have this capability where they're no longer limited by their training cutoff date. But as I mentioned, using a retrieval augmented generation, it also gives you that finer control over what it is actually accessing, as opposed to the entirety of the internet. You have a very tight, controlled pocket of data that your LLM is getting, and so you can control that, which just again improves the accuracy, reduces the hallucinations, which is really what this is all about.
Yeah. And building on that, again, the key point is, with grounding and RAG, you can provide that non-public information to the LLM. And that's really what we're seeing across a lot of customers who are experimenting with this and grounding these models with knowledge graphs. But something we also want to touch on as well, or at least acknowledge, is fine tuning. You may have heard about this. There's really two main approaches to, taking a foundation model and improving the performance. First is grounding, which we will be focusing on. And again, that the key topic or the key point there is incorporating that non-public data with the LLM. And we really think that graphs and graph data science are uniquely well suited to create a high quality data set for this purpose. Fine tuning is a second approach, and we see that as complementary, but almost a secondary approach that organizations are taking, because often grounding is the first step. It's the most direct way to give the model access to your information and see a demonstration or a demonstrated improvement in performance. But once you've had success with grounding, that can give you more data, more example questions and answers that you can then use to further fine tune the model by providing it those high quality question answer pairs to help it specialize for your use case. So, fine tuning is a great complementary approach, but today we are going to be focusing on the grounding piece of it. And so before we jump in, just a very high level session summary. Just a couple of ideas to keep in mind as we move forward, through the next hour and a half or so. Grounding, very important approach, and it allows you to take the power of the LLMs and combine it with the insights from your organization's data, whether it's research, financial, customer data, any private, not internal information that you want to make access to the model. You can do so via grounding. And a key point that we really want to emphasize is that this data needs to be high quality. You can't just throw everything into a database and expect improvements from the model. You need to develop a high quality curated data set to make sure you're providing relevant, accurate, high quality information to the model when you want to ground the answer. And as we're going to show, a Neo4j knowledge graph combined with graph data science algorithms are uniquely well suited to this, to build that data set, to log the LLM interactions in the same database, to visualize the performance of the model for explainable AI, understandable AI, very important in highly regulated industries. And then finally, to analyze the LLM's performance and see where can you get further improvement? How can you understand how the model is operating, how customers or users are asking questions of the model, and then where can you find further opportunities to improve? Again, very important for production use cases. And so with that, Alex, do you want to give them an overview of what we've been working on?
Yeah, absolutely. Go to the next slide here. So I think it's really important to understand why we even built this in the first place. So we have a graph data science library here at Neo4j, which can sometimes be difficult to fully understand and use to its best ability. And so we were trying to develop a system that would allow people to easily just ask a quick question, understand like how to apply it to their use case, and really just keep moving forward. And so we started with just asking your vanilla GPT, how would I use this particular algorithm or something along those lines. And we found that it was kind of hallucinating a little bit, wouldn't give clear-cut answers. And this is a lot to do with the training cutoff that we mentioned earlier that a lot of these models have. And so what we ended up doing was we ended up taking a bunch of documentation and putting it into the knowledge graph. And by accessing that, we were able to get very accurate answers. And so we all this was in a notebook at the time. And so we decided to kind of package this all up into a Streamlit front end, which would make it very easy for users to interact with. And that kind of brought us to where we are today.
Yeah, and Alex, just to build on that, we were really,
Hmm.
when you're asking about a specific algorithm, we were, getting hyperparameters that had nothing to do with that algorithm because, again, this was referencing, documentation that was almost 2 years old at the time. Obviously, some of the knowledge cutoffs have changed and continue to move, but when we started working on this, you were getting parameters for an algorithm that had nothing to do with it, and that's just not helpful. You'd almost be better off not asking the question. So it was interesting to see how much better those answers were, even with just public documentation.
Yeah, absolutely. And so this is just a little snapshot of our application. So this is where you can control the parameters that you're using for your LLM. And so we allow people to choose their model and kind of experiment with like what kind of responses they're getting. We allow people to set the temperature, which basically allows the model to go from a deterministic to sort of random, more random, I should say. And we also allow for the grounding, which is, that retrieval augmented generation that we were talking about, where you can go to 0 documents used to kind of create that LLM response, which is basically just like using the LLM out of the box. Like you just go to the ChatGPT website, or you can decide how many documents do you really want to use to generate that response. And that has implications on the processing time potentially, and as well as, that token length, or the size of the data that you're giving to the LLM. And so this application also allows us to log the conversations that users are having inside of the same graph that all of our documents are located. And this allows us to draw direct relationships between the messages and the documents that are being used to generate those responses, which allows for some really powerful analysis, which is really going to be the core of what we're talking about today.
And a little bit about the grounding data that we used, just to give a little bit more background. What we did was we actually scraped all public data sets. So we weren't using anything internal. We were just using, we have about 1,200, almost 1,200 pages of official documentation from the Neo website. We also scraped developer blogs, articles from the support knowledge base, and some GitHub repos that have additional information and explanation about the graph data science library. So there's a variety of different data types in this, from markdown pages, HTML files. We haven't pulled in any notebooks or code repos just yet, but that is on our backlog. And if you've built or worked with these applications, you know that you take the source documents and then you split them into smaller chunks. And we use LangChain for that, the recursive text splitter. And at the time, we specified a 512 character chunk size. This is actually pretty small, but it was because when we started this project, we were working with smaller windows in the LLMs. You could see from the prior page, those have expanded up to 8K and even 32K. And I'm sure it's just going to continue moving in that direction. But we started small because we wanted to have really, you have to be careful about how much text you're passing back and forth because your answers can get cut off in the process. So we created these text chunks and then created embeddings using GCP. We support multiple models, but a lot of this application was built on GCP infrastructure. And what we did when we were creating those text chunks is we also made sure to include the URL source, whether it was the official documentation, a blog, or a GitHub repo. We wanted to have that source so that when the model provided its response, it could actually cite its sources, because they don't always do that out of the box. But we wanted to make sure that whatever advice it was providing, it could link back to a specific source so that someone could then follow that link and get a little bit more information. And before we get into the actual, graph-based analysis, I did want to touch on one key point we wanted to highlight, and this is based upon something that we learned along the way, where a key theme of this presentation is going to be data quality, and that starts with the actual source documents and the chunks, even before you create embeddings to add to the database. And what we found was, with our initial chunking strategy, we were actually splitting the documents on characters that didn't exist in all the documents. And so on the left side here, you can see the distribution of the text chunk size. And remember, we're targeting a very small text chunk size, but we had to put it into log scale because you can see we have 3,000, about 13,000, and all the way up to almost 34,000 characters in a single chunk of text. And if you have chunks of text that are that long, they're never going to match to be provided as context. And even if they did, they would overwhelm the model, especially when we were back using 2,000 and 4,000 context window sizes. And so the data quality and the exploration starts with your source documentation and with the initial chunks. And this is where traditional NLP and EDA techniques can be really valuable, even before you're creating embeddings and loading them into a database. And so you can see when we corrected the chunking strategy, we had a pretty good distribution. I mean, it's not a perfect bell curve, but it's what we would expect. Most of the documents are around that 512 that we were targeting, but because of just overall document length and different splitting methods, we have some that are smaller or larger. And as we get more into the presentation, we'll show you how we evaluate and curated the data set to make sure it was efficient and high quality. So with that, the next thing we'll do is we'll walk through the data model. This is all going to be on a Neo4j knowledge graph. And so Alex can walk you through what we have as a data model.
Yeah, absolutely. So once we chunk up the data, we load it into the data model. And you can see in the purple there, we have the document nodes, which represent all of these individual chunks. And these are tied to the URL, which is just where they were. So that could be just a link to the Neo4j documentation webpage. And these documents, we ran a nearest neighbors algorithm on them using the GDS library. And that's where we get these similarity relationships that are just telling us, how similar are these documents to each other. And then we also have just a lot of other properties on here. The community and the PageRank scores are also from GDS algorithms doing community detection and also node centrality. And then we also keep track of the embedding and the text. And then just a couple other things that really help us get a better idea of what's in these documents.
And as we move through the presentation, we'll go into all of those, how we generated those specific properties from GDS. That's going to be a lot of what we cover. So it's just a bit of a preview here.
Yep. And then if we move forward just a little bit here, we can see when we implement logging, so this is what we add in addition to the knowledge graph. And we can see here that we have the user sessions in red, and these capture everything that happens from the time a person logs in to when they close the web page. And then so you can have multiple conversations going on, and these can be with unique LLMs, or maybe you just reset the chat to see what happens when you clear the memory buffer. And then of course we have the messages. And so these are just sequential nodes of question and answer. And so all of the response messages will also have context relationships with those documents that are used to generate the response. And so that allows us to, again, do some really powerful analysis down the road. And we're also capturing here a lot of the parameters that we use in the LLM response generation to kind of get a better idea of how can we better optimize this, or maybe we want to lean towards a particular model for our use case. And we also, it should be noted, have a rating option where the user can rate the response that they get from the LLM, and that really helps us get a better idea of how this is functioning, and we can really get a lot of implied quality ratings for the documents and communities as well, which we'll go into later.
That's great. I mean, one of the just really unique aspects of this is the fact that we can have the logged conversations in the same database as the context documents and their sources with these persisted relationships. That's really the value of a knowledge graph, is that it's not just the messages, the message objects themselves. The relationships are objects in the database, whether it's a context relationship or a similarity relationship. Those are objects in the database that we can analyze and use to visualize and understand the algorithms and how they're operating, and really lean towards, was explainable AI. there's a lot of questions about LLMs and how they generate their responses. But if you're leveraging a knowledge graph with a schema like this, every single conversation can be traced back to a document and to a source to know where the LLM got that information and how it produced that output, whether it's for an internal user or an external facing user. And that's we'll emphasize this a couple of times in the presentation, but this logging in the same database with the documents and the ability to visualize the entire operation really sets knowledge graphs apart in this regard. And so with that, what we want to do is pivot a little bit and focus on the first part of the knowledge graph, the documents and their sources, and emphasize how important it is to have these high quality grounding documents if you want to see a noticeable improvement in the performance of the LLM. And so to start with just a little kind of a high level background, if you've been involved with data science or machine learning for the past decade or so, you may have come across Andrew Ng, a prolific researcher, scientist, and businessman out of California and Stanford, who did a lot to really promote early use of neural networks and big data. But now, over the past year or two, he's been shifting the focus to promote data-centric AI. Whereas over the past 10 or 15 years, the emphasis has been on bigger data sets and improving models under the assumption that if you have enough data, that data engineers and data scientists and algorithms will figure out something productive to do with it. The change now is to focus on curating higher quality data sets in order to improve model performance. And these higher quality data sets very well might be smaller than kind of the collect everything big data approach that has been used until recently. And if you think about retrieval augmented generation, this is basically data-centric AI. The large language models are trained on massive data sets, and those data sets are too large to practically curate or evaluate to make sure everything's high quality and accurate. But they're useful in the fact that they do represent often the internet and public data sources where the data will be of mixed quality. Anyone who's worked in a large organization knows the challenge of getting good, clean data. But what we can do, and what we're focusing on in this presentation, is improving the LLM response by grounding it on a typically smaller but very high quality data set. And we've seen this is a major differentiator in the performance of the large language models. And the key is that the quality and the efficiency of that data set, in addition to making non-public information available to that model to use to answer questions. You're using the capabilities of the model, but focusing it on your internal non-public data. And in fact, what we've seen through our testing, and one of the reasons that we have the option to turn on and turn off grounding in our application, is that low quality data can actually negatively impact the LLM response. If you provide it with several documents that aren't accurate or aren't really applicable to the question, the LLM might focus on those documents even though they're not relevant to the question. And so if you're asking it, you might ask it about a logistics question but provide fraud documentation, you're not going to get the answer that you want because that grounding data isn't really relevant to the question at hand. And so this just, we cannot emphasize enough how important high quality grounding data is to enabling your LLMs. And throughout our work and our testing, we came up with five themes or 5 elements of high quality grounding data. And the first is just what we were saying. Is it relevant? Is the data relevant to the purpose of the application and the questions that you expect your users to ask? This might seem obvious, but part of it is you want to make sure that you focus on the most relevant information. This isn't a big data use case where you throw everything into the grounding data set and hope for the best. Rather, you want to focus on, if it's about a certain application or a database or an operating system or even a business topic, you want the data in the database to be relevant to that and what you expect your users to be asking about. And if you're using the crisp DM model, this is kind of the business value, or what's the business use case for the application. From there, you also want to make sure that the data is augmenting. LLMs have knowledge gaps. They're trained on these large data sets, but there are limits to those. And there's two main reasons that LLMs typically have these knowledge gaps. The first is, we've touched upon a few times, is a lot of data is not public or wouldn't be available to these models for training. And so they wouldn't know about sensitive internal research or R&D efforts inside an organization or a government agency. So they're just never going to have knowledge about that specific topic. But there's also a time frame gap where, previously a lot of the models had September 2021 knowledge gaps. Those are continuing to move up, but the models are unlikely to ever be real time. And so it might be something that happened after a current training window where, again, the model just isn't going to know. And especially if your use case is really time sensitive, real time or near real time, the model is never going to be retrained to catch up if you need data available immediately or within, say, an hour or 15 minutes. So make sure that you're augmenting whatever those known gaps are in the LLM's knowledge. The next is reliability, or is the data reliable? Does it have accurate information? And this could be whether it's an internal or external data source. If you've worked in a very large organization or government agency, quite often there are multiple sources of the same information, and some are more reliable than others. And so if you're pulling contract data or user data, are you pulling it from the source of truth or whatever the most reliable, most up-to-date source is, because you don't want to be providing inaccurate or unreliable information, because that's going to be reflected in the quality of the answers the LLM provides. Next, is the data clean? Is there going to be noise or extra characters? And we'll get into some examples of this as we move forward, but you want to spend some time curating that data set to find, if you're scraping websites, are you getting extra metadata or extra code that will potentially take up space in the context windows going back and forth to the model? You just don't want to have that in your data set. And if you're scraping notebooks or code repos, are you taking functions that are the functions complete and whole? You don't want code cut off or to be spliced. You just want to make sure that the code and the documents and whatever you have is as clean as possible. And finally, efficient. Do you have duplicate information or near duplicate chunks that are going to take up valuable space in those context windows as well? This is another thing we're going to show in a few minutes, where if you're scraping information about, in this case, algorithms in the graph data science library, you might have the same piece of text several times. This makes perfect sense on a website, but when you're scraping everything into a database, you don't need 15 or 20 copies of the same text. It might even show up twice as context, again, taking up valuable space that could be used for either other information or for additional text coming back from the model. And you'll see as we go through the rest of this presentation, we're going to label some of the different slides with these 5 characteristics to try to tie it back to kind of this thesis of what you should be aiming for when you create a grounding data set. And so as Alex he mentioned what we did once we loaded the data. We did some traditional pre-processing and exploratory analysis, created our embeddings, and then loaded them into the knowledge graph. And then we started to use the graph data science algorithms to create relationships and generate new insights into this data. As Alex noted on the data model, the first thing we did was create some similarity relationships using k-nearest neighbors. And we ran this on the actual text chunk embeddings themselves. And so we were able to create and persist similarity relationships among all of the text in our database. And you see that here in the graph to the right. The green or gold icons here are the source URLs. And then the red icons are the individual text chunks themselves. And you can see we have a lot of these text chunks pointing to a source, but then they have similarity relationships among each other. And you can see Some have a lot of similarities, relationships with each other. Others are a little bit more different, a little bit more outlier in the data set. But being able to visualize this, if you take it on a broad scale, can see where the documents fit in relationship to each other, and then we'll open up other analytic opportunities that we'll explore next. To gain some additional insights, we ran a community detection algorithm, in this case, label propagation. And this is an algorithm that works really well on a dense similarity graph. And what the purpose is to add some structure to what is largely unstructured data. In this case, identify communities among the context, the grounding documents. Find little pockets that are tightly related to each other based upon the strength of those similarity scores. We also ran a centrality algorithm, in this case, PageRank, a weighted version of the PageRank, which also provided some statistics for each document, where how influential or how strong or how important is this document in the graph compared to other highly important documents that it has a strong relationship to. And once we had all that, we actually generated more embeddings, in this case, node embeddings, on the entire graph of our context documents that will allow us to visualize our entire database and be able to analyze and start identifying areas we might need to look at and inspect to produce a high quality grounding data set. And what's really important about this is, we have a relatively small data set here, 1,200 documents and 15,000 chunks of text. This is a small data set to start, but we're going to be expanding it considerably. And if you think about a large organization implementing a grounding data set like this, you might have those documents to a factor of 10 or 100 or 1,000. And so you need EDA and data quality tools that scale. And applying these algorithms with some traditional text analysis, as we'll show, is a solution that scales. It's a very unique, highly applicable and practical solution that can scale across massive data sets to help you find errors and outliers and near similar documents to improve the overall quality of your grounding data set. And that's the key. These approaches will scale to extremely large data sets in organizations. And so what we have right here is actually a 2D visualization of our graph, of the embeddings from our graph. And so each icon here in the plot is one of the individual text documents that we scraped and then chunked. The colors on the graph represent the graph community that each document belongs to. And then the size of the icon represents its importance, calculated by the PageRank score. And so you can see that a lot of the communities in this graph are fairly distinct. We don't have colors overlapping. There's a few here and there, but in general, what we're looking for, and it's an eyeball test with a picture like this, we're looking for clusters of icons that are distinct from each other, tightly clustered, and have a single color. And where there's color overlap, that's something we might want to investigate to see, do we have good embeddings? Is there a quality or a question about the actual text or the embedding of the text that is causing the overlap? Because we want these communities to be as distinct as possible and as tightly clustered as possible. So this is a good first place to start when inspecting and evaluating the quality of our grounding data set. And if we zoom in a little bit, this is a very, very close zoom in on two of the clusters in the graph. On the left here, we can see, even though the icons are a little separate here, they're actually very tightly clustered in the overall embedding space. We have one color, which represents a single community of really important documents. We have a larger icons here. Whereas on the right side, and for the presentation, I know the icons are a little small, we see an area where we have a lot of these documents that are actually overlapping in the embedding space. This small piece where we're zoomed in here actually has 5 distinct communities of documents that are either adjacent or nearly on top of each other. The lower corner, there's a mix here in the middle that you might not see. We have a small cluster here, and then all the way curling up here, where there is a lot of overlap, where we would want to investigate what are the documents that have really close overlap And is there a quality issue, or is there, some just might naturally exist, and that's okay in our database. But if we have a lot of overlap, or if we're going to go back, if this was just an entirely mixed up bowl of fruity pebbles, we might want to go back to our chunking and our scraping strategy to see if there's something we need to revisit to make sure we have clean, high quality data going into our grounding data set. And from there, we can actually combine graph and traditional statistics to further investigate these communities of documents in our graph. And so what we have here is a table that we constructed, and this is all in a notebook that'll be published, or it is published and will be made available. You can see how we investigated and created some of these statistics for each community, but we want to focus on the high-level concepts here. What we have is a table of all of our documents grouped by the community in the graph. So each document is assigned to a single community, and then we have a count of how many documents are in that specific community. And from there, we started calculating median statistics to help us find potential errors and outliers. So we have the text length, the word count, the average word length, and the PageRank score. And what we have here that I've circled is a very, very clear outlier in community 7117. What we have are 51 documents with a median text length of 512. That was the maximum text length that we set when we were chunking up our documents. Each document has a single word, and that word has a length of 512. This is very clearly an outlier in our data that we were able to identify by combining traditional text and graph data science-based analysis. And if we inspect it, what the actual documents look like, we can see it's a lot of metadata and some extra code that was generated when we scraped files off a GitHub repo. These were markdown files that we scraped and chunked, and they just had a lot of extra text that we really didn't need. And so this is an important point where if you're combining data from a lot of different document types, it could be PDFs, ASCII files, Jupyter notebooks, Java files, whatever it is, you may need to have a different scraping or ingestion and chunking strategy for each of those different document types. Or if you don't do that, then on the back end, you need to look for any errors, outliers, or metadata that might be kind of gumming up your data set. And so what we're able to do is, because these are all clustered into a single community, and we know that all of the documents are basically the same, we can actually go ahead and delete that entire community from our database. We don't have to go hunting for these one by one. Again, showing that these techniques scale and would become extremely useful if we're dealing with hundreds of thousands or millions of documents in a grounding database. And so that was looking for kind of errors or kind of gibberish or extra text in our database. We also want to make sure that our grounding data set is efficient. And because we persisted the KNN relationships, we can query them and analyze those relationships just like they are any other object in our database. And so what we've done here, and again, this is all in the notebook that's been made available, we're looking for communities with a very high average similarity score. So of all the documents that have been clustered into a single community, how similar are they to each other on average? And what we can see right here is we have several communities where the similarity among the documents is either 98, 99, pushing on 100%. And that's an efficiency issue for our database. And so if we dig into one of these communities, I know it's a lot of text on the slide, but you can see it's the exact same chunk of text all in the same community. But if you look at the URLs, it's pulling the exact same text from a bunch of different pages explaining graph data science algorithms. Again, on a website, this makes perfect sense. We're talking about heterogeneous relationships and how they're fully supported by the algorithm. But in our database, we don't need that. We only, because we're working with graphs and relationships, we can actually condense this into a single node. Whereas we have 17 copies of the same node, we can use an APOC procedure to pass it all of those nodes and relationships and combine them. So we now have that text as a single document linking to all the sources, making a much more efficient data set. Again, we're working with a small data set here, but think about the scaling times 100 or 1,000 times into a large data set, and you wouldn't want the same piece of text showing up 3 times or being provided 3 times to an LLM for context. It's going to take up valuable space for either additional context or the response that the model provides. So again, graphs are uniquely well suited to have very efficient data sets for grounding documentation. And it's very simple to do because we have those persisted relationships and these APOC procedures. And so with that, we can actually move over to talking about how we're logging the conversations in the same database as the context.
Yep. So we're going to talk about logging here. So it's very important that as you're building these applications, if they're entering the production stage, you need to know what's going on under the hood. And so by using the knowledge graphs and by using these GDS algorithms that we've been covering so far, it really helps kind of peel away that top layer so that you can really understand what's going on here. And so you can look at these user interactions with the documents. You can visualize these conversations, which we're going to do in the next slide. And you can really get some unique tools, such as the GDS library, or we're going to look at a dashboarding tool that is very easy to connect with Neo4j graphs as well on the next couple slides.
And that really is the key, is the explainability. And I started my career as an accountant and an auditor. And so there's a lot of questions and concerns about how these models operate, and especially in highly regulated or production environments. And again, it just goes back to explaining how did you come up with that answer. And that'll be so important. And logging, as Alex was saying, logging the conversations in the same database is such a unique value add. We're really excited to share how we implemented it.
Yeah. So just as a refresher, this is the data model that we're dealing with here. So we have really what's important here are the unique conversations, and then the messages, and then those response messages, their relationship with the documents. That's really the core of what we're looking at here, as well as the GDS properties that we created, such as the community, the page rank, and then those similarity scores. So this is just an example from our knowledge graph. So this is an actual conversation that we had. So we can see the session node in green, and then we have the conversation in orange. So we were using the GPT-4, the 8K version. We have that initial user question, and then we have the response, which uses in pink, which uses those kind of more purplish nodes. Those are the documents. And the community that those documents belong to is indicated with that number. And so you can see that this particular response, that first one there, uses documents all from the same community except for one in the lower left-hand corner there, the 1256.4. And now you can imagine a scenario here where the user asks a question to get a response, and it's not quite what they're looking for. And so the user asks the LLM, can you clarify this? Maybe it provides some extra, the user provides some extra context. And so then we get this other response, which shares half of its documents with that initial response, but then replaces some more that can provide possibly a better answer and better help the user. And this is a very common conversation chain that we see here, where documents kind of pop in and out throughout a conversation, depending like when they're most useful. And we can kind of see that visualized in a different way on this next slide. And so here we're looking at the progress of a conversation. And on the x-axis, we have the sequential responses that the LLM is giving. And then on the y-axis, we have the top 20 or so documents that were used throughout this conversation. And we can see when they appear in that conversation. So kind of in the middle there, we have those really dark blue bars. And so there was a document that was used 3 times in a row. in this conversation. But just below that, we have a document that was used twice. And then a little bit later on, it kind of comes back into the conversation. And so this is just a really good way to visualize what is going on in these conversations. How are these documents being utilized? You can pick out like what topics are they really being best used for. And so it really helps us better understand what's going on under the hood here. And so now we're going to talk a little bit about analyzing the conversations a bit deeper.
Sure. And to start, Alex mentioned before, we're going to highlight another piece of the Neo4j platform, Neo-Dash. You may have come across this before. It is a open source, low code dashboard builder designed for Neo4j. Now, what we're going to show here is some high level statistics and what a business user or a project manager or leadership might want to know as you're experimenting with and deploying an LLM application to production. And what's great about this is you don't have to go to another tool or another dashboarding tool to get these high-level statistics to understand what's going on with your application. You also don't need to pull data from multiple databases because we have the grounding context and the conversations all in a single knowledge graph. You can use Cypher combined with Neo-Dash to create those statistics and make sure that business users or other stakeholders can have a good insight into how's the application functioning, what documents are being used, how are users rating and evaluating the responses. We're not going to go too much into Neo-Dash today, but what we would love to do is point you towards a workshop that happened 2 weeks ago as part of the Road to Nodes series, which was an intro to Neo4j and interactive dashboarding presented by one of the creators of Neo-Dash, who's one of our colleagues here at Neo. There's also, if you go off of neo4j.com and Neo4j Labs, there's an entire website for Neo-Dash itself. And so we just want to highlight another piece of this platform that you can use to get you can capitalize on having all of that data in a knowledge graph to get better insights into how the application is functioning as a whole. And then later on, we will dig a little bit more into the actual conversations themselves. Oh, and so with that, Alex, do you want to show the Neo dashboard?
Yep, so we can do just a quick overview of that. So this is just a quick dashboard that we put together for our Agent Neo application. We have 3 sections here. So basically this first section is just looking at user engagement. So how are people actually interacting with Agent Neo? And we can look at the session statistics or the conversation statistics, just get an overview like how many questions are being asked, how long are these conversations regarding like particular models, what is like the most popular model. And here we can see it's the GPT-4 8K, which makes sense. That's the default model that we use. On this page, we can see some more like LLM oriented metrics. So these really revolve around the message response ratings. And so we can see that we have like about a quarter of our responses are being rated, which kind of gives you an idea of how heavily to weigh those responses. We can see response time and things such as this, and there are many more metrics that you can add to this. This is a very dynamic and customizable dashboarding interface. And finally, we have just some knowledge graph metrics, and this really focuses on the documents. And so as Dan was kind of going over earlier, you can have documents that maybe aren't that highly rated, or you can have communities that are suspiciously similar to each other, like with inter-similarity scores. And so you can have this just update as people continue to use your application, as you continue to upload more data into your knowledge graph, and you can kind of populate this with nodes that you may want to take a closer look at, or communities that you may want to take a closer look at to help better optimize your knowledge graph and your application.
I just want to say, I personally, this is one of the things that I really enjoyed about seeing this presentation is everyone's trying to figure out how to evaluate their LLM, like what are their LLM ops going to look like? And I just think this is a really interesting take on it by using the knowledge graph metrics as well, because it allows you to get into what you were saying before about the quality of what you have. So looking at those similarity scores and et cetera really allows you to iterate and develop the LLM over time, and especially what you're putting in for grounding. So I just think this is a really exciting new space to look into as far as the evaluation of it in practice.
And even building on that, what Alex showed on the first tab was, we support 4 different models right now. We have the OpenAI, we have the Google models, and we're going to be adding the AWS models as well. And right now, we're not even doing fine tuning, but as you start creating and fine tuning models internally, you might have several models that users can select from. Google is taking a little bit of this approach, and same with Meta and the Llama models, where you have text generation, chat models, and even code generation models. And so you very well might have multiple tabs for the different models that you support, or just showing how your users are using the chat versus the generation models in your application. And so I've said this so many times, we're just scratching the surface of what this LLM evaluation, and Allison, you were mentioning LLM ops, what is it going to look like over the next 6 to 12 months? But what we have here is a single database and a single platform that captures all of these metrics and captures those relationships among the different pieces of the puzzle.
Yeah, absolutely.
All right, let's see, Allison, can you give control back to me real quick, and we'll keep moving forward. That was great. Thank you very much, Alex. I'm so glad we were able to include that in this presentation. We do have additional statistics as well, and these are statistics that could be on NeoDash or could just be in your analysis as well. For instance, because we have everything logged as a graph, we can evaluate the conversation lengths. And it's been really interesting to see, how many turns do we have? How often are users, they ask a question, how many responses are we getting? And as to be expected, most of the questions are, it's 1 to 2 questions. So it's 4 messages back and forth with the model. But we do have some conversations where they're pushing 15, 20, and even almost 25. And that's interesting because we're also logging not only the conversations, but the response times. You're getting into more of the LLM ops where, Alex, here you can show you've been logging how long does it take the actual LLM itself to respond, if you want to discuss that.
Yeah, absolutely. So we're just tracking, so each sequential response in a conversation, how long is that taking? The actual prompt generation and to retrieve data from the graph is relatively stable. It's always very short. But what we're seeing is that as these conversations get longer and longer, the processing time perhaps is also taking longer. And so this kind of invites you to look at, what models maybe are creating this long response time, or maybe are we hitting rate limits? How does that conversation memory get stored, and how is it being created? So it really invites you to really look deeper into your system and try to optimize those underlying aspects, which don't really reveal themselves until you take a closer look like this.
Yeah, and under the hood, we're using LangChain to summarize, to have a summary of the conversation to date. But as you add more and more data to that, as Alex points out, the time going back and forth from the model, whether it's hosted on Azure, GCP, or AWS, we are seeing longer response times, in part because the payload going back and forth can be much larger than when you're first just getting started. And that's going to be another element of LLM ops. But again, are you able to log that and log the relationships among the different conversations and actually map out and visualize the entire conversation like we did before to see what documents or what elements of that are causing potentially a slower response on maybe one platform or one model versus another? And that's, again, where graphs are going to highlight. You can visualize and really inspect a lot of these details under the hood that don't surface just through normal logs, or until you're actually going through the process of building an application. And so with that, we're going to shift a little bit to some very graph-based analysis. And I think that further is going to show where knowledge graphs and graph data science can really shine when you're not just building a context database, logging conversations, but then seeing, okay, how is this behaving, and what can I learn about the behavior of my model to iterate and improve the overall performance and the customer satisfaction. One thing you can do, again, just by having all of these elements in the same database, is visualize how are the documents being used. And so this is an updated version of our document graph. It's just a small piece of it, but it shows the actual documents here in the reddish, kind of pinkish reddish icons. And then the brighter pink icons are the LLM responses themselves. And so what we're seeing is a different version of what Alex showed earlier, the different responses pointing to the documents that they used. And this is just a small snippet of the graph, but you can see there's a natural clustering, a natural centrality inside this graph where you have these documents that are really highly used among different responses, but others that are a little bit more, they're still frequently used, but a little bit more so on the periphery. But again, visualizing these natural clusters that occur because we have those relationships as objects in the database is something you can't get any other way, and really understand and interpret how your model is behaving. And so again, a lot of text on the slide, I know, but I thought we would show the most frequent documents that are being used. And you can see the first one is about degree centrality, the most straightforward algorithm in our graph data science library. From there, no surprise, Apache, Spark, Kafka, and some of the BI tool connectors, we use those almost every day, helping to connect Neo to other database platforms for data engineering and ingestion purposes. And then, no surprise, we're getting some GPT, LLM related questions, and then some general questions about data science and graph data science in our Python client, which almost every single one of my customers use as a primary way to interface with the database. So no surprises with some of the most popular and most commonly used text chunks. But what we can actually do is further enhance that by looking at what are the communities, what are the document communities that are most frequently providing context to the database. Because again, we can't look at every single individual doc if we have tens or hundreds of thousands or even millions. We need to group them, and we were able to create those communities early on in the process. Now, for anyone who follows graph data science and the Neo4j developer blog, it should come as no surprise that Tomas's blogs are very popular. We made a point to include those in our data set because he does such a great job. And in fact, that was proven out because Tomas's blogs are the #2 source of content for our foregrounding documentations. The #1 source is the GDS, the actual GDS manual itself, no surprise, but with Tomas's articles, again, coming into a close second. And so for there, what we finally want to take a look at are the LLM responses. And this is kind of the third piece of the database. We started with the grounding context, and then we logged the conversations. But now we want to analyze what responses are the LLM giving us, or what responses are the LLMs giving us to understand and apply some of the same graph-based techniques to understand how are our users using it. What are the good answers, the bad answers, and what insights can we get from that generation we're getting from the large language model. And so we can actually analyze these as a graph or use a very common graph workflow. And because we have the responses and the context together in the same database, we can use some really interesting graph-based approaches. And so what we have here, I'll walk through this step by step. First, what we did was we created a bipartite graph. And that's the graph we see right here on the left, where we have on one side, we have all of the responses that the LLMs have provided across all of the sessions and conversations. And then we have a one-way relationship to the context documents used for each one of those responses. And so it's response to context in that one-way relationship. And what we're going to do is apply the node similarity algorithm. And what that algorithm does is it creates a similarity score among all of the responses. And that similarity is based upon this graph. What are the common context documents that are used to generate the response? And so what this is going to tell us, if we move to the similarity graph on the right, is that these individual responses have different levels of similarity based upon the context used to generate the response. There's other factors we can incorporate in this, but we wanted to start with just a simple, very graphy approach of how similar are the responses based upon the context used to generate them. Because this can give us some really good insights to how relevant and how high quality the different context documents are, and help us see, maybe we have some outdated or inaccurate context that might be affecting the responses. And so what we do is we create the projection, create the bipartite graph, and then use node similarity to end up with a homogeneous graph of just responses and similarity scores among them. And from there, we can use the similar approach we used with the initial documentation. We can identify communities, which we see here represented as the colors. And then we can also have a PageRank score, which is the influence or the importance, represented as the icon size. And this overall graph is developed from FastRP embeddings of just those responses. And so what we see here, we don't have nearly as many responses as we do the context, but we actually have some pockets of different responses that we're getting from the LLM. Why would we want to do this? Is because when we have an application that might have thousands or tens of thousands of responses, we need to cluster them or put some structure around them to look for trends and analyze them. For instance, we could have pockets of responses that are all rated very high or all rated very poorly, or use similar documents that we need to update or we knew that were outdated. It's providing us more insights into what the LLM is giving to our users and to us as we use the application. And so what we have here is a table, and all this analysis is available in the notebook that we're publishing. We have the communities of LLM responses. And so we provided some structure using the graph data science algorithms. And then we counted how many responses are in that individual community. And then we started calculating some statistics. How many context documents were used? What's the page rank? How long is the response that was provided by the LLM? We may have some communities with very short responses or really long responses. If there's too much context, the LLM might not have the capacity to transmit a response. So we look for outliers there. And then, as Alex mentioned, what are the ratings? How many positive ratings? How many negative ratings? Or were there even any ratings? We added that feature midway through our testing, so not all of our documents are rated. But if we actually dig into the responses themselves, there's a lot of text here. Don't worry about reading it. The key point is these responses were clustered together because they all mention graph data science and then the open source libraries NetworkX and PyTorch Geometric, which we see is very often a gateway into graphs and graph data science. You come across PyG or NetworkX in grad school or at a boot camp, or you're just out in the open source community. Great tools, but often our customers are graduating to the graph data science library after getting a first exposure. And so, it's interesting to see we're getting a lot of questions about, how does GDS fit in with NetworkX and PyG, or how do I import into GDS from PyG or NetworkX? It was just really interesting to see those types of responses all clustered together in our top community.
I just wanted to say one quick thing is the other thing I found really interesting is when you were showing positive responses and negative responses for the different communities of responses. I think it'd just be such a great thing to be able to go in and look at those and say, oh, why are these scores not as consistent in this one area? And I think, like we said before, what where you're looking at is, especially for us, if you're looking at it from a product perspective, not yeah. So in that last line, I think you had 4 bad responses, 5 good. So
Yeah.
obviously there's something about those responses that are similar but are unsatisfying. So what does that tell you about the documentation that you have? Or maybe it's something that people are looking for and there isn't a clear area. So I think for me, whether it's an HR chatbot or a product chatbot, it gives you an opportunity to not only see, from a product analytics perspective, how people are using your product, but it allows you to really have a much better understanding of how they're thinking about your product
Yeah.
and where they want it to go. And so especially because you're using it in the knowledge graph, it allows so much more depth of understanding than you could if you were looking at them at a row level in a traditional 2D matrix.
Yeah, exactly. And I'll repeat myself from before, we're just scratching the surface. And that's a really important area of, whether this is included in the Neo dashboard or elsewhere. What are the ratings in these different communities? And are you starting to see communities of responses where it's 10 bad to 1 good, or even 50-50 isn't really what we're aiming for. We're aiming for this 15 and 2 and 6 and 1. This community right here at the bottom, the 5 to 4, that's starting to be concerning. And so because we have a graph, we can look at the responses, and then we can, this is a community of responses that are using the same source documents. And so do we need to trace back? Do we have, maybe there was an update to a library or an update to an application? We're providing older code that might be, maybe there was a breaking change that came out. And so the code that's provided or the answer that provided isn't appropriate to the most recent version of a tool or a software. Any of these reasons could really dig into why we have lower responses. But again, that goes back to the LLM ops and how you can have all of this in a single application or in a single database and do this type of analysis, especially as we're just getting started rolling out these LLM-based applications into production and into organizations. And so with that, we are, as far as the actual presentation, we're going to wrap it up, this part of it, and then we have some time maybe for some questions and a few other things. But to go back to the key points we started with, grounding is a great technique that allows you to combine the capabilities of these LLMs with insights into your organization's data. And I hope we've been able to communicate how passionately we feel about high quality data is essential for deploying these applications into production, particularly in large organizations and governments where you need to make sure this is a well-performing, high value-added application. And to do that, you need that high quality data, which Neo4j and graph data science are uniquely well suited to help you create. You can develop, curate, and manage that high quality grounding data set using techniques at scale. You can log the LLM interactions in that same database, which opens up so many opportunities for insights and analysis. And because these are graphs, you can visualize the LLM interactions and the grounding data to further understand and interpret how your application is behaving. And then finally, analyze those outputs, analyze the responses in the same vein as the grounding documentation to, like we were just covering, identify where there might be lower quality answers or less satisfactory answers, and then identify and mitigate and make sure your application is improving and providing more value, whether to internal or external customers. Now, one thing we did mention early on is that we did publish a lot of the code, and we have some other resources available. Allison's going to make this link available in the chat. We'll also make it available on when this is posted to YouTube. But we have this GitHub repo. It has links to the public code for Agent Neo that Alex published. We also have links to a blog and a public repo from our colleague, Adam Cowley, who created a very similar tool for our Graph Academy website, where as you're working through Graph Academy, you can ask an LLM different questions or get guidance along the way. And he actually went into a lot of detail about how he created that application. And so he did a fantastic job with this article. If you're curious about how to create an application grounded on a knowledge graph, highly recommend Adam's blog and repo. I referenced a notebook a couple of times that's published in this same repo. It's an extensive, more data science focused notebook. And it's not something that you would just copy and use. It's more of a guide for a workflow, and then you can pull out pieces of the code and then apply them to your application. And then finally, we've published 3 blogs so far, and we're going to continue publishing about the importance and different aspects of the context data, as well as other lessons we've learned building this application, and as we're going to be moving forward, continuing to update this application. Right now we're doing it's called a Context is Everything series, but we're going to be writing about a lot more of these topics just to capture those insights and share them with you, so that our entire goal here is for you to go out and build your own application, but try grounding it on a knowledge graph and see how this performs, and the additional value and insights you can get by having those graph structures that might not be available from a different type of grounding database. And so with that, this part of the presentation, I think we've covered everything. Allison, Alex, thank you so much. This is a huge team effort. Thank you everyone who's watching now or in the future. We hope this was valuable. And if you have any questions, we have the chat going right now, or also please feel free to reach out to us. The easiest way is sales@neo4j.com. It'll get routed to us. Doesn't have to be a sales question by any stretch. It's just a good public email address to use. And we hope we can help you build these types of applications using knowledge graphs. Alex, anything else?
No, I think think you covered it pretty well. But yeah, this is exciting to present, and yeah.
Gentlemen, thank you so much. I love this presentation. I think one of the other things that struck me is this idea that your grounding data set is something that needs to be maintained. It's not a set it and forget it kind of situation. You really need to always be on top of how it's being used and making sure that things are relevant. And also how easy it is to maintain a graph database and to include or exclude nodes. I think also is something, the flexibility of graph and the ability to manipulate it is really helpful as well. So thank you so much for all of this. As we mentioned, we put the link into the chat. It will also be available on YouTube. And I guess that's it for us for today. Thanks so much, guys.
No, thank you very much. Thank you everyone who attended, and yes, go forward and build.
Bye all.
Yeah, thank you everyone.
Take care.